This podcast is on quantum numbers. Each electron in an atom has a unique set of 4 quantum numbers which describe its probable location in the atom. Those 4 quantum numbers are the principal quantum number, which is called the energy level quantum number, the angular momentum quantum number, which is often called the sublevel number, the magnetic quantum number, which is also called the orbital quantum number, and then finally the spin quantum number. Now, in order to exactly pinpoint the most probable location of an electron in an atom, those 4 quantum numbers must be assigned to every electron. And each set of 4 quantum numbers for an atom are unique. So according to the Pauli exclusion principle, no 2 electrons in an atom can have the same set of 4 quantum numbers. So every single electron in a particular atom will have its own unique set of 4 numbers. Now let's take a look at each one of these quantum numbers. The principal quantum number, generally symbolized by the letter N, it denotes the energy level in which the electron is located. So when you do an electron configuration and you say 1s2, the 1 in front of the S is the N. That's the energy level, the principal quantum number. Here's a visualization of at least the first 4 energy levels. Now the shapes may not be correct there because it's really the sublevel quantum number that determines the shape. But in general, this is a pretty good depiction. Nucleus in the center, energy level 1 is where N is 1, energy level 2, N is 2, energy level 3 is where N is 3, and energy level 4 is where N is 4. Now, if you wanted to really quickly calculate the number of electrons in each one of those energy levels, you could take the energy level number, the N, plug it into this equation here that you see on the screen, and that would give you the number of electrons. So most students know that the capacity of the second energy level is 8. So that's the maximum number of electrons you can put in there. So if you take the N equals 2, you plug it in for the N in our little formula. 2 squared is 4, times the 2 in front is 8. So the capacity of the second energy level is 8. You could also do that with N equals 3. You would end up with 18. You could do that with N equals 4, and you would end up with 32. So that's a quick little how many electrons are in the energy level kind of formula. Now the second quantum number is the angular momentum quantum number, also known as the sublevel number. Now this also determines the shape of the orbital. It is generally symbolized by a lowercase scripted L. And if you notice in the diagram there, it determines the fact that the S sublevel is spherical, that the P sublevel is dumbbell shaped, and that the D sublevel kind of looks like flower petals. And then the F sublevel also has a rather unique shape. When L is 0, so when the angular momentum quantum number is 0, that letter designation then is S. When L is 1, the letter designation is P. When L is 2, the letter designation is D. When L is 3, the letter designation is F. And as of right now, we don't really have any elements that fill up any more than just those 4 sublevels. Now, the magnetic quantum number, also known as the orbital quantum number, it determines the orientation of the electron's orbital with respect to the x, y, and z axis. So if we look at the diagram here, in the first portion of the diagram, the px, that's the orbital oriented around the x-axis. The second one is the orbital oriented around the y-axis, and the third is the orbital oriented around the z-axis. If you put all 3 of these together, you have the P sublevel. There would be then 2 electrons residing in each one of these orbitals. So 2 electrons in each, you have a total of 6 electrons in P. Now, assigning the numbers, the N, the L, and the M sub L are all related to each other intricately. The N can only be whole numbers, so starting at 1 and then going infinitely. So technically there's an infinite number of energy levels that could contain electrons. The L quantum number, the angular momentum quantum number, the sublevel quantum number can be any integer between 0 all the way up to n-1. So for example, if n is 3, L can be either 0, 1, or 2. L equals 0 being the S, L equals 1 being the P, L equals 2 being the D. So in the third energy level, n equals 3, you can have an S, a P, and a D sublevel. Now, the m sub L, which is the orbital quantum number or the magnetic quantum number, it can be any integer between negative L and positive L, and 0 included in there. So, for example, if your L is 2, that would be the D sublevel. M sub L can be negative 2, negative 1, 0, positive 1, positive 2. 2 electrons into each one of those orbitals, so a total of 10 electrons in D. So a couple things to note from all of this. Number one is that the three quantum numbers, n, L, and m sub L, are intimately tied together. Another thing to note here is that depending on their value, that determines the number of electrons in the sublevel and then ultimately the number of electrons in the energy level. Now here's a chart that kind of ties together all four quantum numbers, at least for the first four energy levels in an atom. So if we take a look, for example, at energy level 3 there, where n is 3. When n is 3, L is 0 all the way up to n-1. So in the L column, we'll have a 0, 1, 2. The 0 corresponds to S, the 1 corresponds to P, and the 2 corresponds to D. So we have a 3S, a 3P, and a 3D. Notice the one above n equals 2, there is no 2D. That's because when n is 2, you cannot have L equals 2 also. So no D in the second energy level. So really the number of orbitals and the number of sublevels are all, directly tied to the values of these quantum numbers. Now, back to the third energy level. When you're in the 3s sublevel, m sub L's only possible value is 0. That is because S is where L is equal to 0. M sub L then equals negative L to positive L, just 0. So you have one orbital. When you drop down then to the 3p, that's where L is equal to 1, M sub L equals negative L to positive L with 0 in between. So negative 1, 0, positive 1. So you have 3 places for electrons, 3 orbitals, 2 electrons in each. Total number of electrons then would be 6 in the p sublevel. Drop down there to 3d, that's where L is equal to 2. So m sub L is negative L to positive L. So negative 2, negative 1, 0, positive 1, positive 2. So there's 5 possible values for m sub L, 2 electrons in each. So a total of 10 electrons in the D sublevel. So the capacity of a sublevel is directly related to the value of the m sub L. And then the m sub L values are directly related to the L values. The L values are directly related to the N values. And this table attempts to sum all that up. Now, spin quantum number is rather easy. It's simply a plus 1/2 or a negative 1/2. So when you draw an orbital diagram and you have an up electron and a down electron, one of those is plus 1/2, the other one is negative 1/2. This particular quantum number is not as directly tied to the other three. And we're not going to look at, the reason for the negative 1/2 and the positive 1/2, just that they happen to be opposite in spin. Now, all of these help us to put electrons into orbitals, but keep in mind that an orbital is just where there's a high probability of finding an electron. And on the screen, we can see the S orbital in the first energy level here represented. Now, the S orbital has a spherical shape, as seen in this diagram. And the origin is right there at the center, and it's around the 3 axes, so it's a 3D space. The p orbitals are dumbbell shaped, so we have each of the 3 p orbitals, 2 electrons into each, total of 6. Notice the dumbbell shape of the p orbital. The d orbitals get a little bit more complicated. Notice that there are 5 of them, 2 electrons in each for a total of 10 electrons. You are not responsible for knowing the shapes. You're just responsible for knowing that the S shape, the P shape, the D shape, and then finally the F shape seen here in the diagram, the F shape is very different than the other three. Notice there are 7 F orbitals, 2 electrons in each, so a total of 14 electrons. So this podcast attempted to introduce you to quantum numbers.